Swayam Prabha. Digital India. Educated India.
So, welcome to the lecture on remote sensing and GIS application in agriculture and NRM part 2. So, we already in this particular topic we have discussed in 2 lectures. One was introductory, then part 1, and today is part 2. Today in this lecture we will be discussing some GIS applications, GIS and remote sensing applications through some case studies, through some real examples and some studies which have been reported in the different type of publications, journals or report. So, these case studies actually will give you a real kind of a understanding that how actually remote sensing and application of GIS tool can help us in the assessment of natural resources and how actually you can represent those information for larger public. So, when we talk about natural resources and especially utilizing remote sensing and GIS tool, one thing often comes into picture and that is land use and land cover. In brief we call them as LULC. I am sure many of you might be knowing about these terminologies. Land use and land cover means any surface cover on the ground which includes vegetation, built up areas, water bodies like lake, river or any stream, mountain, transportation networks or any other thing which are there on the ground. The attributes are measured by remote sensing techniques which are related to land cover and from which the land use can be inferred. Okay. So, in this slide you see 2 nice picture. These are the result of remote sensing data and then application of GIS tools. Now, this is a land use land cover changes in Greater Guwahati area, means where actually our institute, my institute is located, IIT Guwahati. So, a study was carried out to see that how land use and land cover change in the Greater Guwahati area in Assam. This is just to give you an real example. And you see here that there are various sections which blue color means water body in 2008, okay, and then we will come to 2009. For time being, please focus on 2008, how actually it used to look at. Water body blue color, dense vegetation green color, red is habitation means where people live, yellow barren land and this bright green as you see is agriculture land. Now, try to focus on the agricultural land because agricultural land needs agriculture purpose, need natural resources like fertile soil, water, etc., etc. You look at also little bit on the red part on this map and then vis-a-vis try to see compare with 2019 very recently. You can see the area of the red color is quite significantly increased in 2019 from 2008. Some you can see that the agricultural area particularly in this point, if you see that large amount of agricultural areas still were there, but they are not here. But taken by whom? Taken by habitation. That is one worry. Okay. Also, if you come here in this particular corner and compare with current situation, here also you can see that the red patches have taken over this particular agricultural area, right. Now, you look at the percentage coverage of area, you can see that in 2008 the dense vegetation was 51%, here it is 40% in 2019. Look at the increase of habitation, it was roughly 26%. Habitation means houses where people we live. So, it was only around 26% in 2008, but by the time it is 2019, it is 43% almost. So, imagine that how increase of population in Assam is actually taking a toll on the agriculture as well as the green area, right. Look at the agricultural area, around 6%, which has become here in the 2019 has increased to 9.5. Now, there is one point that I would like to discuss especially. Now, two pockets I have shown you where agricultural land has been partly taken over by habitation, but there is one part where agriculture has suddenly increased, and that is the point is here, this corner. Now, where from agriculture comes here? Agriculture comes here in the place of dense forest. So, dense forest has been cut and then agriculture has come in. Now, this is also a point of discussion. There are several debates is taking place, across the country and world, that is it a good idea to convert forest area into agriculture area? Is it a good idea that agricultural areas converted or occupied by habitation, as you see in this particular study? Now, these all actually are point of dialogues, discussion and policy matters. Now, for that kind of discussion, GIS and remote sensing helps, because when you present this kind of comparative picture of 2008 and 2019, then for the people who takes decision at the parliament or at the assembly, policy makers, lawmakers, they can easily get the clear picture differences in the 10 or 12 years, and then they can take a call, no, we are going in a wrong direction, so we should correct it. So, GIS and remote sensing helps you for this kind of exercises. All right. Another example I will give you on LULC, and that is from West Bengal, Sundarban area, very famous. We know that it is famous for mangrove and also many others very vulnerable ecosystem. Again, there is a study carried out by group of researchers, and as you see, look at this particular table. 1975, after 15 years 1990, again after 15-16 years in 2006. So, every 10 to 15 years how the area, that particular area of Sundarban is changing. Now, for this also remote sensing GIS helps. There are few categories: dense mangrove, open mangrove, agricultural land, bare earth, non-agricultural land and water body. So, these are the color symbol for each one of these 6 different types of LULC. And now you look at the percentage change over this every 10 to 15 years. Now, one good thing here, you see dense mangrove area is increasing, open mangrove is getting reduced, agricultural land got reduced little bit in 1990, but again has come back. Bare earth means where nothing is there, no vegetation, from 3 it has increased to 7 and then again gone down to 5.6. Non-agricultural land almost 2%, around 3% and then around 3.5%. So, that is increasing, because with the increase in population, food demand will increase, then people they will get into agriculture for their livelihood. So, certainly you will see a change in the area of agriculture. Water body almost more or less same, a little bit of change has taken place, between 1975 and 2006 in the 30 years. So, in a sense, in this area, mangrove area, I think that system has done reasonably okay job, because you don't see huge differences, I mean negative impacts on the particular this ecosystem. So, as you see that map wise you can present these particular data sets in a very nice manner. So, people again, when you present it in a picture form, then it is very easy to understand what is happening in particular area. Now, the same data sets you can also present in bar diagram, and bar diagram gives you much clearer idea that how over the 30 years how the different ecosystem is changing. Look at here the same data sets, it is much more easily to understand. Dense mangrove area is increasing, which is a good thing. Open mangrove is reducing, but not that significantly. Agricultural land going up and down. So, that means there is a kind of a regulation or regulatory change is taking place. Bare earth also has gone up and then again coming down. Non-agricultural land also almost non-significantly increasing. Water body, there is a little decrease in the water body. So, that may be because of various other reasons, but overall it is not that alarming as of now, as you see from these data sets. But our point is not that. What I am trying to share with you is that how remote sensing and GIS can help you to understand a system what is going through. Next example from another part of India, another ecosystem, Maharashtra. Okay? And here the example is that before and after a dam has been created, how this will affect a particular ecosystem. This map is 1996, before a dam has been created. You can see lot of greenery, right? Lot of agriculture is taking place. Of course, there is barren land, that area is like that, but you can see lot of green patches, is not it? But if you see the forest area is very sparse here, here, here in this zone, particularly in this patch. Okay? But otherwise, agriculture is quite clearly visible in 1996. Settlement is concentrated largely in these few pockets, okay, in a sparse manner. Now 2016, okay, after 20 years, 2 decades, how things have changed, especially after the dam has been created. This data table will give you much clearer idea, but here you can easily see that the green component agriculture has drastically got reduced, settlement has increased. You see here, here, here. So, these are the some new areas where settlement has come up. Okay. Water body, you can see here in this figure only in 2 pockets is visible clearly, but in this picture you see a new water body, that because of the dam, and that is why the dam has been created. Okay. So, water body has got increased, but normally anticipate that when water body increases, so agriculture will increase, but here you see that earlier it used to be agriculture in this area. Look at this picture here. Now, this area has come barren, but dense forest has taken place here. Agriculture has gone out. The alarm is that even after your dam, the barren land has increases. From the picture, it is visible. Now, let us see the data. 1996, 2016. Agriculture clearly visible, around 33% almost, come down to half, 16%. Water body, very less than 1. Here it has increased. Of course, dam has done some good job. Barren land, it was 54%. Now it has increased by almost 3 to 4%, 57%, right? So, that means this is a concern. Settlement, around 5%, increased to around 11.5% almost, quite significant increase. Forest, as you saw that the dense forest has come up here, this is one good signal, but the concern is here, settlement and increase of barren land. If dam is there, you anticipate that there will be more agriculture, but somehow that has not taken place. Few more example on LULC, Jhansi, Chitrakoot, Panna. Now here this particular maps it shows talks about different type of crop. So how different type of crop actually you can actually present through GIS and remote sensing using different colors, because that again will give policymakers a very clear cut idea about what is happening in a particular area. So in this exercise all the Rabi crops for all these three areas has been taken exactly same time, so that you can compare with these three different places at a time. Same season, same type of crop has been taken, almost same similarity. So let us now see that how in three different places they are differently distributed. Let us take wheat for example, greenish color. You see lot of wheat here in this picture, relatively less here and far less here, right? Next the chickpea, okay, all three has chickpea. Now this from picture you can clearly see that concentration of chickpea, even though in a very small pocket, but looks very high in Panna, very sparse in Jhansi and Chitrakoot. Overall area you can only understand when you see the numbers in a data in table form, okay. This helps you to understand the area, which area the distribution is high and how it is actually spread over the entire area. As you see here, here it is sparse, here also chickpea is sparse, but clearly in Panna it is concentrated in this pocket. There must be some reason for that. So this is how things helps to understand. Now here this is the table that I was talking about to look at the chickpea. All right, in chickpea we just now saw that your Panna has concentrated this area, these two Chitrakoot and Jhansi has sparse. So let us see that how it is. So chickpea in Jhansi around 37,000 or 38,000 roughly area in 38,000 hectare, Chitrakoot 16,000 hectare, Panna you see that 80,000 hectare, right. So this is clear from the picture also that Panna is concentrated heavily in this pocket for chickpea. This is how remote sensing and GIS can help you. So you can actually take the information, you can collect and collate from a long distance. You need not to go to the particular area. Sitting here in Guwahati, I can actually through remote sensing and GIS data can actually analyze the present situation of anywhere in India. That's the beauty of this technology. Next, what actually we use for this kind of mapping, what technique? So the vegetation indices or index is a single number that quantifies the biomass or vegetation, okay, for each pixel in a remote sensing image, that image that we get from satellite. So in each pixel the vegetation index is a number that quantifies the biomass of the plants or vegetation. Vegetation indices or VIs are combination of surface reflectance at two or more wavelengths designed for highlighting a particular property of a vegetation, okay. If you recall at the very beginning of remote sensing first introductory lecture, we discussed about different kind of reflectance, right. So VI actually helps us to understand the crop biomass or plant biomass. VIs also gives reliable spatial and temporal intercomparisons of terrestrial photosynthetic activity, and this also will give you the canopy differences. So suppose a plant is a large biomass and has huge canopy, you can easily differentiate from VIs, vegetation indices, that where you have a big plant and where you have a small plant on the basis of the canopy as well. Mathematically, vegetation index compares the number of absorbed light, okay, which are coming from different wavelengths, as for example visible range, infrared, whatever that we have discussed in the previous classes. vegetation indices are designed to maximize the sensitivity to the vegetation characteristics while minimizing the confounding factors such as your background reflectance from the soil or the directional effects or atmospheric effects. In atmosphere, if there are lot of moisture or dust particle, aerosols, so they will also affect. So finally, the measurements of this vegetation attributes include your leaf area index LAI, percentage green cover, chlorophyll content, green biomass and absorbed photosynthetically active radiation, which we call as APAR, is a very important phenomenon in the field of GIS remote sensing, APAR. Okay? Now, how we calculate all these vegetation indices? All right? Each one of these has different formula to calculate. Now, let us start with the simplest one, RVI or ratio vegetation index. RVI we can calculate with this formula rho NIR by R, where NIR is near infrared wavelength and R stands for red. Then we have DVI, difference vegetation index. DVI you can calculate through this formula rho NIR minus rho R, again near infrared minus red. Then comes the most heard about in a popular index, that is NDVI, normalized difference vegetation index. Most of you might have heard about this. NDVI is calculated using this formula rho NIR minus rho R divided by rho NIR plus rho R, where the NDVI value is lied between 1 and 0. Next comes soil adjusted vegetation index or SAVI. Now, SAVI we can calculate through this formula, same where rho NIR minus rho R divided by rho NIR plus rho R plus L. Now, what is L? L is the correction factor for your soil brightness. L, if is 0, very high vegetation cover. If L is 1, then very low vegetation cover. Okay? Enhanced vegetation index or EVI, you calculate using this formula, G rho NIR by minus rho R, rho NIR plus C1 rho R minus C2 rho B plus L. What does this means? B stands for blue, C1 for 6, C2 7.5, L1, G is equal to 2.5. For wavelength, when you calculate your health vegetation, so then you get EVI value between 0.8 and 0.2. Otherwise, the EVI value will lies between +1 and -1. Okay? Next, OSAVI, optimized soil adjusted vegetation index. Here L value we considered as 0.16. Transform vegetation TVI, same you use NIR and R wavelength value rho NIR minus rho R by rho NIR plus rho R plus 0.5, and then you calculate the TVI from NDVI value. Basically, you get NDVI plus 0.5 square root of that value. Then comes vegetation condition index or VCI. Again, you use NDVIs to come to VCIs. NDVI, J stands for that NDVI for jth month or jth week. NDVI minimum is a long term, like as for example 30 years of minimum NDVI for jth month, a particular month or week for continuous 30 years. Suppose you have taken say July of any year, 30 years you have observed that July month data only. NDVI max long term, again for 30 years. Here maximum NDVI for jth month and week that you calculate. VCI is 0, then poor vegetation, VCI is 50% when fair vegetation, VCI is 100% when you have optimal vegetation. Okay. So, next comes modified soil adjusted vegetation index or MSAVI. You can calculate utilizing this formula. This is pretty simple, you only need NIR and R. Then comes NDWI, normalized difference moisture index. Okay. So, NDMI, again you can calculate using this very simple formula, where SWI means for short wave infrared and NDMI value ranges between -1 to +1. Okay. Next, vegetation difference water index, NDWI, again you can use it from NIR data. Here PGG stands for green surfaces, green water surfaces, where you calculate the flooding or the humidity conditions of NDWI. You consider value between 0.2 to 0. In case of water, surface water, you calculate it and you consider it the value between 1 and 0.2. Moderate drought or non-aqueous surfaces, you will have 0 and -3, and if it is drought means where there is moisture is almost negligible, the value is -3 and -1. Between that range it actually stays. So, next comes GEMI, Global Environmental Monitoring Index. You can calculate using this formula, where again near infrared and red wavelengths information works quite nicely. Next comes Normalized Difference Red Edge Index, NDRE. Once again here near infrared information helps you. Now red edge index, actually you carry out it for soil or land health condition monitoring. If you have bare soil or just crop is about to grow, NDRE value will range between -1 to 2. Unhealthy plant or immature crop, suppose you have crop in a very immature stage, then your NDRE value will be between 0.2 and 0.6. Healthy, mature or ripen, mature harvesting stage, then your NDRI value will be between 0.6 and 1. So, if you get NDRE value in that area, then your crops are supposed to be in healthy, matured or almost ready to be harvested. So, the RE value, the range age light, is considered between 715 to 7 nanometer. Okay. Now, so many vegetation index I mentioned in last couple of minutes. So, for you it is just that you try to just remember some of them, that these are the different indexes. To understand the applicability of this, you need especially remote sensing or GIS course for that. Now, all these vegetation indices like RVI, this has the potential to indicate the stress level of crops due to, suppose its high correlation with the leaf area, dry biomass and also chlorophyll content. RVI can give you some indication that in that corner of a field there is some problem, the plant is going through some stress. So, even not going into the field, you can actually tell that this is happening. DVI, it helps in distinguishing between soil and vegetation or crops or plants, but it does not account for the difference between the reflectance and the radiance caused by the atmospheric effects, various atmospheric effects or shadows for any region. Okay. So, that it cannot give you. NDVI is a dimensionless index, okay, and it describes the difference between the visible and near infrared reflectance of vegetation cover, and NDVI can be used to estimate the density of green area on any place. How much area is actually green, NDVI helps you, and that is why I said that NDVI is one of the most popular index in remote sensing. People use it. NDVI also helps differentiating bare soil or barren land from grassland or forest or plants, vegetation. Okay. It can also helps you differentiating between different crops and crop stages. Suppose rice, transplantation stages, green, maturity stages, golden yellow. So, you see, it can clearly capture that through NDVI. NDVI values, as I said, that it ranges between -1 to 1 with negative values indicating clouds and water, Positive values near 0 indicates bare soil. Higher positive values ranging from 0.1 to 0.5, it gives sparse vegetation. And if you have dense vegetation, then it will be above 0.6, greater than 0.6, but can go up to 1. NDVI is also the most commonly used vegetation index to assess water stress, but it uses narrow bands and that overlap with the chlorophyll features of a plant. Okay? NDVI is also used for drought monitoring and famine, early warning and so on and so forth. NDVI increases with the increase of soil moisture because water has a low reflectance in red but almost negligible in NIR reflectance. So, the difference will be small and largely negative. So, the sum also will be small, right? The sum also will be small and NDVI large and negative. Okay? So, what happen is that if in the field, suppose if you irrigate the field or suppose rainfall suddenly takes place in an area, automatically you will see that you are getting higher NDVI. So, that is an indication the moisture level has suddenly gone up in a particular area. Alright. Then EVI is almost similar to NDVI and can be used to quantify the vegetation's cover, greenness, density of forest. This also helps in correcting some atmospheric conditions. In remote sensing, atmospheric condition is a very important aspect, okay, because its reflectance can be affected by the different constituents in the atmosphere. The background noise also can be corrected by using EVI. NDVI is chlorophyll sensitive, whereas EVI is more responsive to canopy structural variation, and that includes your leaf area index, canopy type, plant physiology, canopy architecture. EVI has also improved sensitivity to high biomass region, forest area, with improved vegetation monitoring. The atmospheric effect, as just now I said, that it gets minimized in case of EVI. Transform vegetation index TVI. TVI is commonly used to monitor vegetation cover. It largely helps eliminating the negative values and transforming the NDVI histogram into normal distribution. Okay. So, it helps in normal distribution. TVI cannot be calculated when your NDVI value comes -5 or less than -0.5. Next, NDMI is used for determining the vegetation water content. NDWI is strongly related to plant water content, and that is why NDWI can be used to understand if plant is going through under water stress or not. So, to understand in a field, suppose rice plant, we all know it requires so much of water. If there is less water and plant is running out of water, NDWI can help you to give an early warning. NDMI moisture index general value ranges from 0.685 to 0.154, whereas for the same condition NDWI value ranges from 0.146 to 0.444. Okay. Then NDVI is more sensitive to chlorophyll content in the leaves, whereas NDWI is sensitive to the water content in the leaves, and that is why if plant is running out of water, NDWI will be better index. Optimized soil adjusted vegetation index, OSAVI, we discussed through previous slides that it uses a standard value of 0.16 for the canopy background adjustment factor instead of 0.5, which is generally used for SAVI. Okay. Modified soil adjusted vegetation index, again it is designed to substitute NDVI and NDRE where they fail to provide us accurate data due to suppose low vegetation or a lack of chlorophyll in the plants. In that kind of condition, MSAVI will help you. MSAVI also minimizes the effect of bare soil on SAVI. Okay. Then comes GEMI. GEMI is almost similar to NDVI, but it is less sensitive to atmospheric effect. GEMI is more affected by bare soil, and that is why GEMI should not be used for areas where vegetation is very less, most of barren land. GEMI may not be a good index to use for. NDRE, normalized difference red edge index, is a method of measuring the amount of chlorophyll in the plants. It can be used generally in the mid to late growing season when the plants are mature. Imagine the rice field. Okay, I am sure most of you know about rice growth stages. It takes around 90 days. You transplant very light green and then it tillering stage deep green. So rice 90 days it gives clearly different stages. So NDRI is used generally in the mid to late growing season when the plants are mature and ready to be harvested, and when the chlorophyll concentration is relatively higher. And during this time your other vegetation index would be less effective. Only NDRE can help you in such condition.